Hello everyone. Okay, so in this video we're looking at proof by induction, but we're looking at the divisibility proofs of induction. So what these essentially are is we're just trying to prove that a certain function or term or anything is always divisible by a certain number. So if we look here, proof by induction, the 9 to the power of n minus 1 is divisible by 8. So it's the same steps as before. So we prove true for n equals 1. That's the smallest value of n. So it's 9 to the power of 1 minus 1, which is equal to 9 minus 1, which is 8. And that is divisible by 8, so true. Now we assume true for n equals k. So I have 9 to the k minus 1 is equal to. Now I'm assuming that this is divisible by 8. So I would just write this as 8a. So that just means this can be written by as 8 times something. Now, when I'm usually doing the divisibility ones, we usually kind of have a power. So what I tend to do is I kind of usually just get that power on its own. So I write this as 9 to the k is equal to 8a plus 1. Right? So there's my assumption. Now, finally, prove true for n equals k plus 1. So something in here. N to the k plus 1 minus 1. Now I need to show that this is divisible by 8. So I rewrite this now as 9 times 9 to the k. Then using my assumption, so see here, I have a 9k here. And I said 9k is equal to this. So I'm just going to use my assumption and sub that in. So I'm going to have 9 times 8a plus 1 minus 1. 9 times 8a is 72a. 9 times 1 is 9 minus 1. That is going to be equal to 72a plus 8. And then finally, what I realize here is I could factor out an 8 here. I could factor out 8, and then I'm left with 9a plus 1. So therefore, this can be written as 8 times something, i.e. 8 is divisible by it. So then you just include your little line of proven true for n equals 1, assume true for n equals k, which implies true for n equals k plus 1. Therefore, proven by induction for all values of n. Element of natural. That's it. Right, let's try another one here. Prove by induction that n squared plus 15n plus 4 is an even number for all values of n. So remember, an even number just means it's divisible by 2. So what you can just do here is, so prove true for n equals 1. So 1 squared plus 15 times 1 plus 4, which is equal to 1 plus 15 plus 4. Which is 20, and 20 is divisible by 2. Can that be written as 2 times 10? Tick. Now we need to assume true. N equals k. So I'm left with k squared plus 15k plus 4 is equal to, now I'm assuming it's even, so I'm just going to say 2a. It can be written as a multiple of 2. Now we need to prove true for n equals k plus 1. So I'm left with k plus 1 squared plus 15 times k plus 1 plus 4. This will multiply to k squared plus 2k plus 1 plus 15k plus 15 plus 4. Now, what I realize here is my assumption is I'm assuming that k squared plus 15k plus 4 is divisible by 2. So gather them 3 terms here. And now I'm going to replace these 3 terms with 2a. So I'm left with now 2a plus 2k plus 1 plus 15, which is plus 16. And then I see here, oh, I could factor out a 2. And I'm left with a plus k plus 8. Therefore, I have proven for n equals k plus 1, it is also divisible by 2. true by induction for all values of n elements of natural numbers. So make sure to include your little statement at the end because you will lose a mark. Now let's try one more here. Prove by induction that 13 to the power of n minus 6 to the n minus 2 is divisible by 7 for n greater than 1. So we need to prove true. So remember, this is for the smallest value of n, and the smallest value of n here is n equals 2 because it's greater than 1. So sub that in, 13 squared minus 6 to the power of 2 minus 2, which is 13 squared minus 6 to the power of 0. So 169 minus 1, which is 168, and that is divisible by 7. 168 divided by 7 is equal to 7 times 24. So ding dong, proven, right? Next, we assume true for n equals k. So 13 to the k minus 6 to the k minus 2 is equal to 7a. Now, usually I'll get one of my powers on its own. So I'm just going to get this 13k on its own. 13k is equal to 7a plus 6 to the k minus 2. And now I need to prove true for n equals k plus 1. And that is going to be 13 to the k plus 1 minus 6 to the k plus 1 minus 2, which is going to be k minus 1. And now I need to show that this is divisible by 7. So I have a 13k plus 1 here. So I'm going to rewrite that as 13 to k times 13 minus 6 to the k minus 1. So this is going to be 7a plus 13 6 to the a minus 2, or sorry, k minus 2. Right. Now 7a plus 6 to the k minus 2. I'm timesing it all by 13. Minus 6 to the k minus 1. So this is going to be 13 times 7. 91. 91a plus, so this is going to be 13 times 6 to the k minus 2 minus 6 to the k minus 1. So this can be written as, here's a bit of a tricky one. So we have some manipulation to do here. Now, I need to find a way of combining these two terms here. 13 times 6 to the k minus 2 minus 6 to the k minus 1. Well, what I could do is I can write this as 91a plus 13 times 6 to the k minus 2, right? And then I also could write this as 6 to the k minus 2 plus 1. So I'm left with 91a plus 13 to 16 to the power of k minus 2 minus, now use this 1, rewrite this as 6 times 6 to the k minus 2. Then I have 13 6 to the k minus 2s minus 6 6 to the k minus 2s. 13 minus 6 is 7. So I'm left with, that's 91 there. So I'm left with 91a plus 13 minus 6 is 7 6 to the k minus 2. I can factor out a 7 here, and I'm left with 13a plus 16 to the k minus 2. Therefore, I've proved my induction that this is divisible for all values of n greater than. Right? So that's it. Just make sure to include your little steps there. So that one was a really, really tricky one. Right? So I hope this video was some help to you guys, and I'll catch you guys later. Bye.